Venu sir, can you make me as a co-host?
Done, sir.
Sir, am I audible to everyone?
Yes, sir.
Okay. Fine. Sir, is speaker 3 is joined?
So what is ID, sir?
Fayaz Ahmad Sofi sir.
Fayaz,
Fayaz Ahmad Sofi.
not yet joined.
Okay. Okay, then I will. Good afternoon, sir.
Yes, good afternoon.
Yeah.
Am I audible?
Yes, sir. Yes, sir. You're audible, sir. So good
Yeah,
afternoon.
please.
Okay, sir. Good afternoon to
Yeah.
all. Welcome to the second day of 5-day online FDP program on AI&ML for smart sustainable solutions in civil engineering. So without further delay, I would like to invite M. Mohan Rao sir to introduce today's speaker.
Yes.
Okay, thank you, sir. Good afternoon to one and all. Now I would like to introduce speaker of the third session, Dr. Fayaz Ahmad Sofi. Dr. Fayaz Ahmad Sofi is currently working as an assistant professor in the Department of Civil Engineering at National Institute of Technology, Srinagar. He holds a PhD from the University of Nebraska, Lincoln, USA, and he did masters in structural engineering from the Indian Institute of Technology, Bombay, and graduated in civil engineering from the National Institute of Technology, Srinagar. His prime research areas are finite element simulations, behavior of steel structures, steel girders, system level behavior of steel girder bridges, hybrid and composite tubular columns, machine learning applications in civil engineering. Dr. Fayaz Ahmad Sofi has published more than 20 research articles in international journals, presented his work in more than 20 national and international conferences, and guided nearly 50 students for their PhD, Master, and BTech projects. He handled more than 40 consultancy projects and funding projects as principal investigator. He has also delivered expert lectures at faculty development programs, conferences, and workshops, and also received various awards and honors from prime institutions for his contribution to academic and research work. Now I would like to hand over session to speaker Dr. Fayaz Ahmad Sofi sir.
Thank you, Professor Rao, and thank you all organizers as well as the attendees of this FDP program. First of all, I would like to thank you for inviting me for this program. And thank you for nice introduction too. I think it was really good, way more than really I think it is. So, sir, is my screen visible? Is
Yes,
it fully visible?
Yes, sir.
No, sir. No, sir.
I think this should. I'll just check once. So please check again. Is it fully visible, the full screen?
No, sir. Just wait, sir. I will ask. Venu, sir.
Sir.
Sir, can have you given permission to
Yes, sir,
Dr. Fayez, sir?
I have given you.
No. Yeah. Okay. Yeah. Oh, just wait. Yes, sir. Now it is visible, sir.
Yes, it's fully visible. Okay. Thank you very
Sir,
much.
sir, one more thing, sir. Venu, sir, can you mute all the participants?
Yes, sir.
Okay. Sir, you can proceed, sir. Thank you.
Sir, Fayaz, sir. Fayaz, sir.
Yes, sir. Please, little louder, sir, because I'm unable to hear the sound from there. I mean,
Okay,
I
okay.
don't know why it is.
Accidentally, I make you as a host. Can you make me as a host?
Okay. How to do that? Okay. Show host on.
Indian Geotechnical.
You're sharing, screen sharing.
Achha, co-host. Should I make co-host or host?
Make host, sir. I will make you as co-host.
Yes, I have made you back. Okay.
Yes, sir. Okay. Okay, now.
Yeah, now you can proceed, sir.
Okay, thank you very much.
Just you can. Sorry,
Venu, sir, is there any issue?
Fayaz, sir. Make your audio unmute.
Unmute. Okay.
Yes,
Sorry, sir. Is it now? Is everything okay now? Screen
Yes,
is
sir, everything
okay.
okay.
Yes. So I welcome everyone again. So I hope that all of you have listened me during the introduction part. And thank you, Professor Rao, and all organizers as well as attendees. Today I will talk about committees of artificial neural networks. We have learned a lot, or we must have used the machine learning in one form or the other form, because this is one of the hot areas which has almost infiltrated every discipline. So, but very less people are aware about the committees of artificial neural networks. Should we use artificial neural network as just one network, or any other machine learning algorithm as one algorithm, or should we use it in combination with its similar sister algorithm or multiple algorithms? That is a question, whether it has advantage or not. Those are some of the areas of research that need to be investigated. So today I am presenting a couple of studies that I have done Actually, the one other study that I have done is on an actual bridge inventory. This study was done in United States while I was a student that time. So I have done it that time. We call this as a committee of artificial neural networks, so that we studied the behavior of bridge using these committees. Now, I'll quickly give my introduction as my research areas. I am basically a bridge person who does research on steel bridges. And recently, some of my PhD students have worked on double skin tubular columns also. We have used machine learning in different projects across the different areas that I am working on. So, among one of the having the background, this background, I want to emphasize here that machine learning could be really an asset for asset management. What is an asset management? For example, we have bridges of the entire country or entire state or entire district. And as an organization, if I am a responsible for that bridge management as head of the unit or as head of the team, then this becomes a really interesting tool. So I am going to, that's why I say that machine learning applications as far as asset management is concerned, especially bridges. So I want to talk about that. Now, uh, to give this background, I would, because I have been allotted 1 hour, it means I would also give a little bit more insight into the bridges. How do really bridges behave at the level when we design them and at the level actually they are, which I will be calling a system level evaluation. So if you look the entire presentation and you want to see that what is the whole aim of this presentation, I have put it in few lines, which basically one of the burning issues in United States is that their infrastructure is old. It's not mid-age, it is over the mid-age, and they want to extend their service lives because it's not possible to replace all the bridges. It's not possible to replace entire infrastructure with a new one. Of course, the feasibility is not there. Economical feasibility is not there. It requires a lot of money, and at the same time, it's also not practical to replace every old bridge with a new bridge. So one of the needs which was there when I was a student in from 2014 to 17, and it's still a very hot topic in the United States. They want to extend the existing service lives of their bridges. Some of their bridges were old as far as the current specifications are concerned. They want to extend them and make them so that they could work for the modern loads. So extend their load carrying capacity, ensure that they have higher load carrying capacity. If the now you know that unlike India, United States has long highways because it's a bigger country than ours, and the entire economy is based on its highway system. So one crippling, because bridges form the critical points in any highway system. If you load post a bridge, what is a load post is, if we limit the load that can go over a bridge, it significantly affects the economy of that region, because then vehicles have to make detour, they have to take the longer routes, it increases the cost, and it also increases the economical development of that area. So this has been a very challenging need that people wanted there to see if the bridges can carry more loads than what they were designed for, or if there is an old bridge, can we provide an extra load to it, can it carry a more load. So a thrust for the more load was there. That was the motivation for entire this research. So now if I come to objectives, what exactly I did, because that statement was overall. So my main objective was, because we had this project from our Department of Transportation from Nebraska State. So this project, they wanted some decision making in their asset management, in their bridge management for their inventory. So that asset management, they want to they were getting some limited grants, and they want to use those money where it is needed. For example, if they want to bridge test, they want to take a decision out of, if there are 1000 eligible candidates for the bridge test to ascertain higher load carrying capacity, which ones should we do and which ones we should not. Because of limited finances, the asset management decisions were very critical. So that was there. So we decided, okay, we can use ANN as a leverage point for taking this bridge management decisions. So how accurate it is, how reliable it should be, that was one of the aims of this small project. Then another two important things that we have realized. One of the professors, Professor Novak, who has developed HL93 vehicle, the design vehicle for the bridges in US, uh, he had done many tests, around 60, 70 actual bridge tests. So I was lucky to use those tests to figure out that actually bridges can have more load carrying capacity than what you design if you take their boundary conditions into account, that what actual boundary conditions are. So then secondly, I also tried to see that if we take system into account, how the load carrying capacity of a bridge will vary. So this presentation today might not be purely an ANN based presentation, which I will give. One third aspect of this presentation would be entirely on how to use ANN for bridge evaluation. But I think two-thirds or about 50% of this presentation, I want to tell more about the system behavior of the bridges and how the system, this bridge can be, this system level analysis can be more beneficial for bridge engineers. If I want to highlight, show the highlights of my presentation, of course, I will discuss first overall I have discussed overall motivation. Now I'll supplement this motivation with some numbers. Then I will discuss the research objective for each one of these three main critical studies which I have pointed out. Then the method of study that we have used, and then we'll of course discuss some of the results. So these are the three studies where I will, first one is I'll show how bearing restraint is an important parameter if you are looking for the load carrying capacity of a bridge. Second, how the load distribution is one of the critical factors. Even our Indian code IRC 6, it doesn't have even load distribution formulae that the bridge engineers can use. We rely always on a refined model, even if we have to evaluate a bridge. Uh, Thirdly, the third aspect is how ANN can be integrated into a methodology for evaluating the load carrying capacity of the bridge. So these three aspects I want to touch in today's presentation. So if we look at the motivation, in US, one interesting part is they evaluate bridges like students in the class. So they will give a report card, ASC, American Society of Civil Engineers. They issue report card every year. And this data was of 2013 because I left in 2017. Then afterwards, I have not updated this because now I'm working on little different areas. That time, the average age of bridge was 42 years in US. It means if you take average, there were bridges, half of the bridges were above 42 years. Normally, we design a bridge for 100 years. So 30% of the bridges have already exceeded, because earlier it was 50-year design life, but new design life is considered to be 100-year. But 30% that time, because I am talking about older bridges, those bridges had 50 years as design life. So 30% of these entire bridge inventory in US has already exceeded that life. And if they would have increased their spending, what they were doing in 2013, if they would have increased that spending by 60% in each year, then there was so much a backlog that they have to retrofit their bridges. It would have taken them up to 2028. These are some of the things which are documented in the report card that ASC has given. So if you look at their national bridge inventory at the US level, 24% of their bridges were structurally deficient. Structurally deficient means those bridges must have been designed for lower loading standards, because in US, unlike in India, the loading standards evolve periodically. I mean, their design load changes from time to time as the new vehicles come, new requirements or heavy loads come. Their design vehicle is accordingly it's new. It becomes new and new. So currently they are designing using HL93. It is the name of the vehicle. It's a hypothetical vehicle that they are using. So most of 24% of their bridges were structurally deficient, means they were actually designed for a lower load. they had the deficiency if we take the current load into consideration. Secondly, some of their bridges were functionally obsolete. I mean, if function wise, if the bridge was designed for one lane and now the two lanes, the road has a two lanes, so it's a functionally obsolete bridge. So so in total, 24% of the inventory was classified as structurally deficient or functionally obsolete, and 42% were designed. Their design load is unknown, or they had lower historical standards. I mean, lower loads they were designed for, and 10% of their bridges were entirely posted. Posted means they had posted the load that the bridge can carry. They had limited the load that will go over the bridge. So in terms of, here is a small graphical sketch. If you can see this sketch. So from this graphical sketch, around, I am talking only about highway bridges and steel girder bridges. Then I am seeing that out of 60,000 such bridges, roughly, you can see that these are different historical design standards they have used. HL93 is the latest standard. You can see 54% of bridges, they don't know what is the load carrying, what for these bridges were designed. Similarly, 12% bridges were designed for HS20. And in the state in which I was, Nebraska bridge, this bridge, there were roughly about more than 3,000 these steel girder bridges, and which are about 21% of the inventory. Then we had there 96% of these bridges were designed for loads less than HL93 vehicle. So, and I am talking, the US does not have just 60,000 bridges. I am talking about load posted bridges. The percentage of load which are posted bridges, where the load posting restriction is there. Similarly, I am talking about load posted bridges in Nebraska, which are load posted bridges. You can see that also. Although 3,200 are highway bridges, out of that, the percentage in the x-axis is the posted ones. So, in nutshell, what I can say is that all those bridges which were posted, steel girder bridges with simple spans, because that is where I limited my scope. I want to take simple bridges, simple span bridges with whether one span or multiple span, but simple spans, simply supported. 88% were among the posted bridges, 88% were in the overall US, and 99% were in the Nebraska, which among the posted bridges, which were simple spans and steel girder bridges. This is the percentage of the bridges on which I was focusing on. So with this motivation, then I went to check, okay, how they are evaluating the load carrying capacity of bridges. The load, evaluating the live load carrying capacity of a bridge is known as load rating. You rate the bridge, how much load it can carry. So we express this in terms of a load factor. So expressing this load rating, mostly they use computational methods. I have checked different departments of transportation of different states there. So most of them were using computational methods. I mean, they had their software developed using finite element or using some tool. And yes, 0.5% they were doing load testing, because load testing is a costly process. You have to test the bridge, how much load it can carry. Accordingly, you can determine its load rating. And few were also done by an engineering judgment by the inspector. So once they did the posting, you can see that 78% of the bridges load tested. If they do load testing, 78% of such bridges, the results of the load testing proved that 78% of the bridges you can carry actually more load than what the analysis gives you. It means basically their load carrying capacity was higher, but the standards by which you are evaluating them or the methodologies that you are using, it shows they are posted, so they have to post them. So if we can open a bridge which is posted, it means we can allow higher load carrying vehicles. It means the economy of the region will boost. These are the benefits if we can open a load posted bridge. So this was one of the motivations for me. Of course, their refined analysis would actually prove that you can open a bridge out of the posting. There are different methods which we can use for refined in the refined category. For example, we have grillage analysis. Then we have plate and eccentric beam analysis. We can use generalized grid analysis. These are different well-known methods in the literature that we see around. Then most accurate among all of them, most accurate is load testing. If we cannot afford load testing because of the cost involved, the second most accurate would be three-dimensional finite element modeling. That's what, if of course, after validating the methodology, we can use it for load testing, and we can uh, probably open some other poster bridges. So this was the major motivation. Another second important aspect of motivation was that how to do evaluation of the bridges. Traditionally, if we look codes across globe, or if we look how the bridge codes or bridge specifications allow us, they say it is to be done by line girder approach. Line girder means we treat a bridge, we treat each girder of the bridge separately. We don't treat the bridge as a whole. If even if we have to design a bridge, we design it by component. Each girder is taken separately. Its analysis is done. Then a line girder analysis is done. Finally, from a 3D to 1D, it is the 1D analysis that we do. This is generic. It's followed across the globe. All bridge codes allow us to do bridge design using 1D analysis, 1D approach. So that's a traditional practice. What if we do our evaluation by 3D? Because although when we are designing the bridge for first time, any conservative approach is okay. But if we are evaluating a bridge which is already at the boundary of what load it can carry, it is better we use as refined approach as possible. There can be nothing better than a three-dimensional modeling the bridge as a 3D and evaluating how much load it can carry. It is as if we take a bridge, load it to until it fills, and say how much load the bridge can carry. There can be nothing better than that. So, but there are challenges involved with some system level analysis. So that was the aim of this entire research. What if we do system level analysis? How that analysis would be different from a line girder analysis, and what would be the benefits that it will showcase? So that's what these three objectives which I discussed initially. That so system level analysis was one of the motivations uh, uh, of this entire research. Then important thing is, obviously system level analysis is costly, whether we do it through testing or whether we do it through finite element analysis, because even finite element analysis is very costly. We need experts, and they need to be in the bridge offices who would be able to do this analysis, and then they need to buy the costly softwares to do this analysis, and it needs a lot of investment. Now question is, can there be a way where we can take an intermediate measure, where we will say, okay, you do your routine analysis, and if needed, we should do this rigorous analysis. So when and how should we do them? That is completely unclear in the literature. It's unanswered question. If we want to do rigorous analysis, how should we do it, and when should we do it? These are the two important questions that form the major motivation of this research. We don't want to do system level analysis because it is costly, but at the same time we want to do routine analysis, which is 1D. But at the times when we want to use the 3D analysis, when should we do it and how should we do it? This research will answer some of these aspects of this question. This was the motivation. So if we look at the student level, what were the objectives? The objectives were very simple. We wanted to develop a reliable and an accurate methodology for predicting the system level capacity of the bridges, so that bridge management decisions can be taken. So in nutshell, we wanted to do a system level analysis without using FEM, without using load testing. That was one of the motivations of this research, so that the costs can be bring down. Of course, before we do that, we need to understand what is the difference between a system level capacity and this element level capacity. What is the difference between the girder capacity and a system level capacity? And then we need to understand that how can a 3D system level behavior be converted into 1D, because the connection between the two is load distribution factor. That needs to be understood. So these were the two motivation major student level objectives, and of course, to do both of them, we need to first develop uh, a FE model, and we need to then validate it against some testing. and that also is a system level, that also is a student level objective. So these were the objectives. They were postulated from top to down, but they were accomplished from down to top. First, finite element model was built as a framework, then load distribution behavior, system level behavior was examined. Finally, the ANN based tool was developed, which could be used for bridge management decision making, where we could tell what would be the load carrying capacity of these bridges. So, if you look, what was the investigative approach? Basically, if you see these stages, these are the years of the, these are the years the way I spend my PhD time. Stage one, the data was collected from different inventories. Then the framework was developed for doing entire research, and this was first year. Year two, the year two was whatever framework we have developed in year one, it needs to be, it was developed in a way so that the bridge office people can use it. Obviously, the bridge, the people in our government departments, they like Excel a lot. So Excel was a focus on the, so Excel is a face, but on the background entire thing was done in Visual Basic Applications programming, so that they could analyze the bridge as a system with all the non-linearities in it, all material non-linearities in it for different loads. Then stage two, what was done was the finite element modeling was done using that tool, and it was validated, baseline validations were done, and the member effects like which are used for load rating, for example, to ensure what is the load carrying capacity of the bridge, ultimately it boils down to what internal load effects are created in a bridge. So if we take example of a girder, it would be bending moment shear force. So we need to have a way out to calculate those from a defined finite element model. That was done for year second. Then year third, system level studies were done where the system behavior was explained. Different system behaviors were explained, including that of the skew bridges, because they are also very common bridges needed as per the geometric implications or requirements. Finally, in the last stage, a tool was developed using this machine learning small, application of ANN, so that this 3D analysis can be replicated by an ANN, which is a black box where you put the bridge geometry, it will give you load carrying capacity. But of course, before we do that, a methodology needs to be developed how we can use it. I still remember when I first time used ANN in this last year, I was shocked on getting the errors of the magnitudes of 40%. You cannot say that this bridge can carry a load of X tons with an error of 45%. That is unacceptable. So then I need, so the need, research need was that to develop a methodology that would be reliable enough to motivate a bridge manager to take a decision that this is the load carrying capacity with some certainty that needs to be done. So that would actually is the what the FDP topic is. It is that what was done in stage four. But overall, I am giving how this was organized. Now, I will quickly, because of the limitation of the time, I'll quickly take first two studies, because there are in total three studies. First two studies I'll quickly go through because they are not the aim of this FDP. They are about system level behavior, but I just want to give a background because this is an interesting study about the background, how system behaves differently than an element, a girder. I just want to reiterate again, this entire study was done on steel girder composite bridges with simple spans. That was the limited scope based on the data. And the reason was because those were the most affected bridges in the inventory. So accordingly, it was limited to that. Now, this study is already published in Journal of Bridge Engineering in 2017. The aim in this first study was we wanted to see that actual bearing restraints which exist, which Professor Nowak evaluated during his bridge tests, how they affect the system behavior. That was the aim of the study. How the ultimate load carrying capacity of these steel girder bridges is influenced by the bearing restraint which is available at the bridges. So that was all. So in nutshell, we wanted to check, we want to propose a methodology because methodology was developed in this paper only, and we wanted to check how much bearing strain is required if we want to account, if we want to consider the system capacity. Is it simply supported conditions are same if there is small change in the bearing boundary conditions? Because the bridge boundary conditions do not remain same. They change over the time, over the lifespan of the bridge. This was an interesting thing. Why this was important? Because most of the bridges that I studied were old bridges. Now, with these old bridges, their boundary conditions were completely different than what they were designed for. Because some of these bridges had metallic bearings, they were rusted, the movements were restrained. So we used those to add to our advantage in evaluating the load carrying capacity of such bridges. Similarly, so this was the aim of that. Now, if you look at the methodology, this entire methodology is developed in Excel using the VBA programming. So it uses two tools. One is VBA and then ANSYS software, because finite element models are to be developed. So what it does is it does entire processing of the data in Excel. I'm sure that if anyone would be interested, I can demonstrate this lively, but because of the limited time, I may not be able to do it in this presentation. I was downloading the bridge drawings from the inventory. That is all what raw data is known as. Then it will go to the second. The VBA program will process it, and it will generate some key details that will go into the finite element software like ANSYS here. The ANSYS will develop finite element model. Finally, entire this all is automated process. It means making a bridge model would have taken seconds for us once this framework was ready. Then finally, we got the output results which were required for our load rating, so that we could evaluate the load carrying capacity of the bridges. There were some issues in the finite element that we needed to explain. For example, because this is a generic program that was developed for the DOT. One of the issues was how to, because most of the loads that come on the bridge are vehicular loads. Now, vehicular loads are applied in the form of a patch as a wheel load. Now, finite element only it does not accept partial loading on an element. Partial traction is not allowed in finite element. So conversion of partial, this, if the wheel doesn't exactly fit on the element, finite element model, then how to put that load, how to make nodal loads out of that patch load. That was one of the issue which was actually taken. Its solution was taken from this paper, which is shown here, and it was implemented in this module which was developed. Similarly, the automation which we did, some of the snaps are shown from there. For example, giving the geometry, meshing, entire thing was controlled in the finite element model. The second thing, some of the material nonlinearities, especially that of the steel and the concrete. The steel was the failure of the steel. It was taken care of by William and Warnke model, and steel was taken care of by von Mises. Then concrete deck was modeled with 8-noded brick elements, and the reinforcement in the deck was modeled with truss elements, and shell elements were used for the girder. Similarly, there are many other elements which were used during validation, especially for contact between the girders and the bridge deck. So then a post-processing module was developed, which actually used the stress calculations at the integration points of each of these elements, and finally used the basic shell theory to calculate the movements, and those movements were eventually converted into a movement of the cross section at each girder using the effective width of each girder as per as2 bridge design specifications code. And this is how they were calculated. So element by element, entire movements were summed up and finally converted into a net movement for the entire cross section of the girder. Because this is a refined analysis, it needs a refined treatment to be done. This all was done in the finite element module that was developed. So for the validation, firstly, the validation was done very simply. You can see keep and feet units here because these are the US units which are used. If we take a simple composite girder and load it, I have as an example, then draw bending moment shear force diagrams. I used my FEA model and the one that we can simply calculate from theory. For, the upper one is simply supported girder, the lower one is a continuous girder. You can see almost there's less than 1% error in this, and that's not an error. That's the difference between shell theory and the beam theory, Bernoulli beam theory. But we can say that theoretical and validation results were pretty dot on these girders. Then going, second validation was done with the actual test. We had a 70 feet bridge, which was built not by me, but my predecessor students in our lab in the US. And then they actually tested it till it got completely destroyed in the lab. So this test was done. So we call it as destructive test. It's a very famous test among the bridge researchers. It's being used a lot. Those who want to validate the 3D system, because you won't often get 3D bridge tests. They are very difficult to get. So this was in our this all data was available in our university. So I used this data for the validation. I modeled the same bridge using the finite element, applied the same loading what those students have applied, and finally when I validated I was able to get entire measurements, load deflection curves what they had measured in 1995. I could do it in 2014, and finally you can see even at different stages of loading, these are the cross section. The second graph represents how the deflections are at the three girders, because it had three girders. At the bottom of three girders, how the deflections varied. We kept it almost everything except at the final ultimate level we could not kept. There was little finite element model showed little less stiff uh, behavior than the actual model. Actual model was a little bit more stiff at the end girders. The reason for that was because real girder had the crash barriers installed, and we didn't model them in our finite element model. It was because of that reasons. Then you can see the load carrying capacity, roughly about 5124 kilonewton was the ultimate load that this bridge took during testing, and FEA prediction was 5226. Uh, Pretty much 2% difference between the two. Similarly, deflections were very close, 175 and 178. Then using the ASTO code, which is the bridge design code for US, we evaluated the capacity and we wanted to see that how good is this validation and how good is ASTO doing. Basically, the difference between testing and FEA was 0.7% if we do the evaluation point of view. I mean, if we evaluate the capacity. And if we do the evaluation with the ASTO, there was a difference between FEA, because any code is conservative. Most of the codes are conservative as far as their approach is concerned. Their equations are conservative, and it is true for every country. But between test and FEA, it was pretty dot on. But between FEA and ASTO code, there was a difference. So what we learned from this was that the phenomena, the test in actual test, actually the load got redistributed. When one girder reached to its capacity, the remaining load got redistributed on the other girders. But this aspect is not honored by different codes, because they don't rely on the ductility. This can be possible only when there is ductility in the system. So this is something that most of the bridge codes across the globe they ignore it. But what we have seen is in FEA and testing, both the methodologies captured it. Then we did another validation. This is also a very famous bridge test, which is available to bridge engineers. And this bridge test is about Tennessee Bridge. This bridge test was done there, and this bridge test was done way back in 1971 by one of the professors, and he provided us the data. Then what we did is that it was a continuous bridge. We modeled it again. It is a four-span continuous bridge. We modeled it again, and eventually, without taking much time, I just want to tell that we were able to capture its behavior perfectly all right, what they have observed that time using our finite element model. And even the difference in the ultimate load carrying capacity was about 1.3%. Load deflection curve was perfectly also captured. So then this was the initial part of this research. Then the remaining part was that where the parametric study was what happens to the system level if there is a boundary restraint. For example, if your bridge becomes old and that old bridge develops, it develops the boundary conditions which are different from design. So many researchers use different theoretical models. I have given a list here, and then there were many field tests which were done, and I have used about 35 of those tests. And then I found that where if we take these springs, the this stiffness was assumed to be zero during design, but when we did the actual tests, and I out of those 35 or 40 tests which were done by this Novak in 2001, who developed HL93 vehicle for US, I found this spring stiffness for each one of these, this total spring stiffness, it was from 30 to 240 kilonewton per millimeter. If we took actual bridges into consideration. Similarly, other study have also shown from 2 to 40. These are available in the literature. So actually, what I want to say is the field tests show that the boundary conditions are little partially stiffened. They are not. They are not simply supported as we think. So can this be used as an advantage for carrying uh, uh, refined analysis of bridges? The answer is yes. Because if you look at this paper, I have seen that uh, I made 11 different cases where the stiffness was varied for these springs. It was taken from 0 to 100. 100 means it will become pin. In the horizontal direction, it will become like a pin, infinite restraint. And as a percentage of that, we what we did is we took for each bridge this k pin will vary because it depends on the system stiffness. So for the bridge which I used this to define this k pin, I found out numerically that it was 5110 kilonewton per mm. If I give this much stiffness, its behavior would be same as that of the pin. So then I defined what is slide bearing restraint. A bearing restraint which is from 0.6 to 5% of this K pin is a small bearing restraint. And exactly it was in line with what Novak has also observed from the field. Basically, in the field, slide bearing restraint gets developed. Then we did parametric study. So it's like this. If we take a bridge, load it, and give this slide bearing restraint, which is a very small, not a pin. We are providing a very small bearing restraint, which naturally develops with the age of the bridge. The load carrying capacity can go up to 41%. And but it obviously it reduces the ductility because now when you apply the compression in the bridge in the girders, the ductility will go down because now the with the additional compression the deck will fail earlier with this compression. So then we have shown that we in this paper you can read in detail. We have shown that basically it does not matter whether we provide a pin in the end, that does not increase the load carrying capacity. What really increases the load carrying capacity is when you place a very small restraint, because what does that small restraint does at the system level mechanism wise is it ensures that plastic hinges are formed at the ends and in the middle at the same time. If such a condition can be achieved in the design, then you don't need infinite stiffness like a pin, you need a small stiffness, and that will increase the capacity up to 50% in bridges at without any much cost. So this is the main aim. Then I have shown some interesting results in it. So here you can see 50% increase in first yield was seen in the load at its first yield happens if we could place 5% stiffness at the pin compared to compared to the fully restrained pin. So then we also evaluated what happens then to the ductility. I want to skip this because it might not be relevant to this current talk. So in nutshell, for this first research objective, we found that 50% of up to 50% capacity can be increased at the yield level and 41% at the ultimate level by providing this partial restraint. This was the main takeaway from this paper. Then there is a second paper. I will not talk about it because I have to talk about committees. I will not talk about it, but I just want to tell that this is another second system level paper where you can see what is load distribution. I want to just give introduction of load distribution. Load distribution is a concept that allows us to analyze a bridge as 1D, which in place of 3D. 3D is the actually what it is, but we are analyzing it as a 1D. If you look at the different equations or methods which are available, one is earlier, when the earlier Astro code, it had S or D as the method to calculate this load distribution. What is the load distribution? It's a factor, what we commonly call in India as load factor, reaction factor. So it's a factor that you multiply to a 1D. If you place the entire vehicle over one girder and get the bending moment using influence line, just multiply this factor, it will give you what actually would be the movement in that girder if you would have done a 3D analysis. So that's what is the difference. So in nutshell, a distribution factor is a factor that we multiply to 1D analysis to get the 3D effect, 3D bending moment, because actual bending moment in a girder would be much lesser than what you would get if you do a if you place the entire vehicle on one girder. So in India, we don't have, unfortunately, these equations, and I am looking for funding so that we can develop them for our code. They are not available in our code, but they are readily available in ASH2. They are available there. Based on the bridge geometry and all these things, you can calculate these distribution factors directly. We in India, we use lever rule often whenever it is needed. Lever rule considers basically hinges in the cross section, and then analyzes the beam, and whatever reaction we get, we place the load what the code allows us at the closest possible spacing. Then the reaction, whatever additional factor we get to the reaction, we use that as a load factor, as this reaction factor, and use that as but that's too much conservative way of doing it. Then there is another methodology is we can use beamline definition. Beamline is actual definition what the load factor is. It means we want a refined value. You take the beam value, multiply it by G, you will get the refined value. What is the 3D value? Another way is that you can measure the strains, or you can measure deflections, and based on that you can do the distribution of truck load on each of the girders. But I will again skip this the study which I have done in this one, because this paper is available in engineering structures. People can read it from there, but I only wanted to introduce then what happens in a system level. I will again skip this. I want to take this third problem, which is again a published problem in structures journal. So here the aim was to develop, can we do rigorous analysis using ANNs by just removing load testing and finite element modeling, which are both refined analysis but are costly. Can we do that? And can we identify an ANN based load rating procedure? So that is the aim which I want to discuss in the rest of the time. Now, let me first if you generally do a load rating, rate a bridge, this is the procedure you follow, and this is what you do. Especially I am taking the reference to the bridge evaluation from US. The evaluation is mostly done either by load test or it is done by analytical ways by using computational approach, as we have seen the motivation. So people go, they observe the condition of the bridge. They go every 2 years. We call it as bridge inspection. We do the bridge inspection. We observe the bridges there. If the inspectors, we provide the rating to the bridge from 0 to 10 scale. If the rating comes less than 5, then it is mandatory that we have to re-evaluate the bridge for load rating. This load rating is done every 5 years. So you can see that if the bridge condition is very bad, it means rating is less than 5. If the answer is no, then they will say, is the bridge posted? Then you don't need to do anything. But if the answer is that is it a damaged bridge, or is it overburden loads, etc., if the answer is yes, then you immediately you see that uh, is is it possible to construct an accurate bridge model using available plans? If the answer is no, because most of the old bridges we don't have even drawings, how can we construct the model then? If the answer is yes, we have the drawings, then what we will do is we will use a load rating procedure what is available with us in the code. Though we will use their load rating procedure, and we will use the analytical method, calculate the load rating. Does the load rating require posting? The answer is yes. If it requires posting, but as I said, when they do the test on this bridge, it showed it doesn't need load rating. That the question is, we cannot have that much money that we do test on every posted bridge. If the plan is not available, then we have no way, we have to do load test, or we have to use some refined analysis method, because we have no plans are available. We have to build the plans, and then we can evaluate the bridge. But if the plans are available and your methodology tells you that it needs a posting, then we gave them these two steps. We said them, okay, then you use our tool, which is an ANN based tool that we are giving. If our ANN tells you it needs a posting, because ANN is an intermediate level between a refined level and a routine level, because ANN itself is not so much reliable. It's an intermediate between the two. If our ANN says you yes it needs posting, then you should not spend any money on it. Just post the bridge. If the ANN says your method says it needs posting, ANN says no, it doesn't need posting, then you can spend money on it. So this important bridge decision, our tool is helping them to do that. Now, this is quickly that I wanted to share the motivation, and quickly about the bridge inventory which was there. In total, 8,000 these multi beam bridges were there. Out of those, roughly steel girder bridges were roughly around 5,700. Out of those, 2,100 bridges were which I targeted, and simple spans were about 5,000. Then out of those 5,000, there even in these simple spans, some of the bridges were non-composite, because these are old bridges. I didn't want to do those non-composite bridges because that required a substantial other things. So I targeted only these 2,100 bridges which were composite bridges. But in my research, I just downloaded 61 bridge plans which I actually visited, and I visited all those bridges because I could replicate using these 60 bridges these entire 2,100. These 61s were uh, they were they were chosen in a way that they had same statistics as is present in these 21 bridges. So as you can see, the sample I am showing here, the rest of the bridges I used in this research, about 254 bridges. Rest of the bridges were hypothetically created which matched the existing population. So this is how because I just evaluated the parameters, took 61 bridges, then I could create the other population that is used in this research done. Now, how is the load rating done? I quickly I'll tell you the formula. The load rating is done if R is the total load carrying capacity of a bridge, then you deduct the capacity which is needed for dead load. So R minus gamma D. Gamma is the load factor. So whatever is the D is the capacity needed for the dead load. So you deduct that, it means remaining capacity would be used by the live load. So I divide it by the live load demand in the bottom. There is a live load factor, and L is it could be bending moment, it could be shear force, and impact factor needs to be used while you are evaluating the live load carrying capacity. This is how the load carrying capacity is done. Usually, ASTO uses a distribution factor. We removed this distribution factor because we said them this distribution factor is based on 1D converting 3D analysis into 1D. It ignores the system level behavior. Instead, we said them, let us do limited 3D analysis. Let's do limited 3D analysis using finite element and then train an ANN, build a model which could be refined with more and more analysis. And these were the bridge parameters which we have used. You can see the span lengths, skew angles, and different material properties which were there. Now, regarding ANN, I am sure that most of us are aware of it. ANN uses inputs which go into the each node, uh, and each connection is provided with a weight. They go to the activation functions. The weighted sum goes to the activation function. Finally, it is input into other layers as an input, and finally it gives us an output. So if you see ANN, the parallelism in ANN, it's something like this. In an ANN, we have a weighted sum, which could inputs could be geometry and all, so that they define each bridge would be a point. Then these weights, if we can find these weights represent the model by which you get the output. So you decide some criteria for evaluating the performance, like mean square error or some any other criteria we can use. So that this is a standard way how an ANN works. So in my study, you can see 254 bridges were made. Out of those bridges, interestingly, I made 3 sets instead of 2. I called one set as design set, which is consisting of 100 bridges. Then I made the remaining bridges, which are 154. All of these bridges are different. 154 bridges, 100 bridges were 54 bridges were, I call them as independent testing set, and 100 bridges were as testing set. There was a reason why I made 2 testing sets instead of 1. Then I will tell that reason in a while. Then design optimization. Then I had to optimize the architecture of an ANN so that it gives the best possible results. So before I go ahead with remaining couple of slides that I have, I want to take the permission from organizers. Is there any possibility that I can extend it by few more minutes?
Yes, sir. Yes, sir.
How many
Yes, sir.
minutes I can get?
Sir, max 5 minutes.
Max
Maximum
5.
5 minutes, sir. Yeah.
Okay. Okay. So I will then quickly take you. I'll just skip this methodology because you can see it from the paper. So because the aim is that architecture. Whenever we are using ANN, we should not blindly use it. The first thing is that based on this research, first of all, we should optimize the architecture. Architecture means how many layers, how many nodes in a layer, which activation function to use. We should do thorough study on that. What should be the size of the design set, means the set on which you will do training? What should be the size of that? Should I use 100? Should I use 50? Because these are heuristic questions that needed to be done. So we developed a small routine that does all these things. That's why I have an independent testing set that tells me, is this the best trained ANN, or I can have some other ANN which is better than this. So so I used 2 optimization algorithms, this training algorithms, Bayesian regularization algorithm and Levenberg-Marquardt. These are the standard training algorithms which are available in MATLAB, which can be easily used for ANN training. Eventually, I figured out that 3 nodes were enough. If I increase the nodes, it just makes the ANN stupid. I mean, it does the overfitting in it. Our ANN should be so that it could do generalization rather than overfitting. So we should not make our ANN unnecessarily strong by putting more nodes into the ANN. That was one thing. Secondly, another important thing, because I am going to make a committee of ANNs, so there was a need to tell how many ANNs should I use in a committee. Again, I used an error to figure out how many of them are needed in this algorithm. I would request the audience that they can look the details from the paper which is published. So finally, we did the load ratings from it. But before doing this load rating, I want to take you to the committee. Yes, I'll show you one yet. Methodology का अच्छा ये. I want to take to this slide, which is a very important slide. So what is an ANN committee? We define ANN committee as group of ANNs which are having same architecture. So for example, you can see that there are 10 inputs, 2 layers. Each layer is having 3 nodes, 3 and 3, and 1 output. So this is a one architecture. Another ANN is having an architecture of 10-3-1. So, and in this, if it is because it's an ill-posed problem, whenever we have ill-posed, most of the problems that we solve are ill-posed problems. So, if we use ANN, the concept of committee is if we want to solve a problem, it is better that we take different experts and train each expert for that his or her specialization, and then ask them to give a fused decision rather taking a decision from one ANN, because that would be always a better decision because it will reduce the variance error which is there. Bias error cannot be reduced, but variance error can definitely be mathematically reduced if we make a committee. A committee decision is always better than an individual decision. So we made 4 subcommittees and we fed the same data to each of these subcommittee. The subcommittee had each subcommittee had 15 members. They had same architecture. That's why it is a subcommittee. So 4 subcommittees has 4 different architectures. But within those, even within a subcommittee, the ANNs differed because their training was done differently. One was trained for physics, another was trained for chemistry, another for history, so that they could make a better decision. This is the way we made a committee. And then we predict the load rating. And we, in our results, we found that this committee approach substantially reduced the error and it increased the reliability of your results substantially. And it could be put to a practical use. So this is one thing that I wanted. The sensitivity analysis I will leave because of the time. So finally, you can see that these 29 were the existing bridges which we never showed to the ANN, and we could get uh, very accurate load ratings which were comparable to the FEM which can took months and months to build the models. So we could replace actually ANNs with the refined analysis with this model. Finally, because I have limited time, how to use this? How can we use this ANN load rating? The question is very simple. If the ANN load rating shows you higher load rating, then what one can do is uh, I showed the same load rating using different methods on these typical 3 bridges. You can see that the FEM showed 24% more load rating. ANN showed little in between the two than what the ASTO is showing. So we can even after doing reliability analysis, which was a subsequent part of this research, we can reduce the load carrying capacity of bridges. We can compensate, we can compromise some capacity, but still we can unpost some of the bridges which are already posted there in the system. So this was about it. And final conclusion is that while it is good to do design using 1D analysis or line gutter analysis, but it is better that evaluation should be done using a 3D system evaluations. But those 3D system evaluations, we can do that either by testing or by developing a refined models, though like finite element models. But those are all costly approaches. To reduce the cost and to do it at an inventory level, one can develop machine learning based models and can improve them. And even nowadays, physics informed machine learning models can be developed, and they extend, and we can extend that them as a powerful tool in bridge management in taking decisions about posting and non-posting of bridges, which has substantial impact on the economy of the area in which these bridges form part of the road network system. Thank you. Thank you very much.
Thank you so much, sir.
Thank you.
Now floor is open for questions. If anyone have any questions, you can interact with the speaker for a couple of minutes. Any questions from participants? or anyone. So you can check for comments in chat box, but there are no questions yet. Any questions or anyone wants to interact with the speech?
Where is the chat box? It is in here.
Yes, sir. Beside participants at the bottom, but there are just at the bottom. If you see participants bottom, sir, go down. Yeah, just beside the participant, you see chat box. Chat.
Okay. Okay,
Yeah,
chat
but
is there.
yeah. There are no questions.
Okay. Yes. If there is any question, I would appreciate to answer, or people can also write to my email. And it's a very interesting area because in India, we don't feel the need of this research area because our bridges are relatively young, and we don't have old bridges. So once the bridge becomes old, then this would be one of the interesting, very, very interesting areas of
Okay, sir,
research.
good afternoon.
Good afternoon, Dr. Arvind. How are you?
I'm fine, sir. How are you, sir?
Thank you so much. I'm good. I'm good.
Sir, we can see that there are many bridges in our India which are built long back ago during time of Rajas, Maharajas. Can we implement this technology for that?
Yes, it is definitely it is for old bridges because bridge evaluation. But you know what we do in India is if there is a first of all we don't do any load rating on the bridges. We do it very rarely when the bridge develops a problem. But in US it is done routinely. It is done every 5 years. So yes, if we have an old bridge and we want to evaluate its load carrying capacity, we definitely can implement this, but it needs to be trained for the bridge types of bridges we have here.
Because we do, if we see old bridges, there is no concrete in that or no steel in that.
Yes, yes, that is true. We need to actually develop those damage scenarios in the finite element first, so that we could actually create a lot of similar bridge scenarios. And because first of all, we have to see whenever you make any machine learning model, it's a garbage if the training data set is garbage.
True.
And another important thing, unfortunately, I could not discuss everything in this presentation. If you look ANN, how it or any machine learning algorithm, how it works, it's basically an interpolation thing, but done in a very nonlinear way, in a highly nonlinear and parallel fashion. So what we do there is, if we can place our design set on the boundary of that multidimensional space, assume that we have a output variable and inputs are plotted as on x-axis, multidimensional axis. We get a cloud. In that cloud, if we can place these design sets on which we train our data on the boundary, then effectively whatever we predict, we are doing then interpolation. Interpolation is always accurate than extrapolation.
That is
So that could be that is where the accuracy of any machine learning model lies. It is very well explained in my paper. Actually, it can be looked from there.
it.
Okay. So, any other questions?
Any questions from anyone?
Good afternoon, sir. Can I have a chat with you, sir?
Sure.
I'm Dr. Sheetal Sare from the structural engineering area, basically. Can this ANN be useful in the health assessment of heritage structures?
It is used a lot for that, because more the problem, the complex it is, better you can do. But only drawback is you need data. If the data is available, then you can use any of the machine learning models. Although I have shown just ANN, there are many other algorithms, but ANN is a very versatile model. Only drawback in this is there must be enough training data. The enough training data is there, then only any machine learning model can be used. If the data is not available, it is to be created using some analysis. The better that data is, the better predictions would be there.
Thank you, sir. Thank you.
Okay.
Okay, then thank you, sir. Thank you once again for your great insightful lecture on applications of artificial intelligence, artificial neural networks in structural engineering. And now with this, we'll move to next session. Thank you, sir. Thanks you once again.
Okay. Thank you very much. Thank you, everyone. Thank you.
Thank you, sir. Okay. Now I would like to invite.
Sorry, just
uh,
for disturbance. Can you, sir,
Tell me, ma'am.
please share your contact details?
Yes, ma'am. Sir, contact details will be shared in the group. Okay, ma'am. I will share you, ma'am. Okay.
Thank you, sir.
Yeah. Now I would like to invite Dr. YBB Sai Kumar sir to introduce our next speaker, Dr. Arvind Kumar sir. Yeah. Hello. Sai sir.
Well, sir. Hello. Good afternoon, everyone. Dr. Arvind Kumar is an accomplished academic and researcher in civil engineering, specializing in structural engineering. He holds a PhD from National Institute of Technology, Srinagar, and has over a decade of experience in teaching, research, and industry collaboration. Currently serving as an assistant professor at Mathrusri College, Engineering College, Hyderabad. He has made significant contributions to smart concrete, structural health monitoring, and sustainable construction materials. Dr. Avin has published over 35 plus research papers in reputed international journals and conferences. He has authored a book on structural health monitoring and holds a patent on self-sensing reinforced concrete for structural health monitoring. His research has been recognized with Best Paper Awards at prestigious international conferences. He also delivered expert lectures at AICT, ATEL, FDP at NIT Srinagar, contributing to the academic and research community. Additionally, he has completed a postgraduate certificate course in artificial intelligence and machine learning from Tribulati Nagpur, enhancing his expertise in integrating AI&ML applications in civil engineering. With his strong academic and research background, Dr. Arvind Kumar continues to contribute to advancements in construction technology, smart materials, and AI-driven innovations in structural engineering. So, Kirpa sir. No.
Okay. Yeah. Now I would like to invite our fourth speaker, sir. You can hand over the session.
Yeah, thank you, Sai, for your kind introduction.
Sir,
Good
sir, your
afternoon to
voice is low, sir.
yeah, now can you hear? Hello.
Hello. Sir, your
Is it
voice is
audible
still
now?
low, sir. Yeah, now it's okay, sir.
Okay.
Yeah, you can proceed, sir.
Good afternoon, one and all the participants. I think participants are busy with classes or some other academic works, so it will be much helpful for them if they listen at least. Because I am not going to tell how the things have been done, I'll tell you how the things will be done. So, starting with that, let me share my screen. I hope my screen is visible. Tirupati sir, can you tell me? Hello.
Yeah, tell me, sir.
Can you see my screen?
Yes, sir.
Okay, let us start with the presentation. We'll have two things, or we'll learn two things today, actually. So now, in today's session, if participant listens, then we can have two things today. Where I can use AI/ML in civil engineering and how to use that. These two things will be answered today with some case studies which we have done for the small things. So what we learn today is introduction to AI/ML. I think few of the speakers already might have introduced. Still, we will go some touch up. Next, we have benefits and limitations. Then we have what are the challenges implementing AI/ML for concrete or research structural engineering or any civil engineering field. Then we have some uh, programming on AI/ML in concrete mix design and strength prediction. Anyway, we are having case studies, real world application, wherever we can do or have done it, followed by future trends and opportunities. So introduction to AI/ML. So what is AI/ML? It's just a branch of computer science that enables machines to perform tasks that typically requires human intelligence, such as learning, reasoning, and problem solving. So if we tell in a simple language, so we are training the computer as intelligence, as if like human being behaves in some situations. So how in that situation computer can behave or it can take the decisions. So we will train that using different models. So machine learning is a subset of artificial intelligence. So how relevant to civil engineering, AML can analyze vast amounts of data, optimize designs and predict outcomes, making it a powerful tool for solving complex engineering problems. So it's just if you tell in simple language, we are training computer to get our problems solved by it with less amount of time and in short duration we can say. What are benefits of using AML or what are the limitations? As even Sophie sir was telling in the earlier presentation, what are benefits? So benefits are its accuracy. So once we train the machine, uh, based on its training, we can get the accuracy. If we are training with perfect data, then we can have good accuracy. Efficiency also can be improved based on the different models. So we have a number of models that we will be seeing in our slides. So efficiency can be improved using different models for different data. We can have cost effectiveness also or safety early detection of structural issues if at all there are there we can detect it before it gets worse. And what are the limitations? The limitations since it is not being used in the vast area because of these limitations. The limitations are data dependency. So to train the model, we should have perfect data in the large amount, not for the small amount. So the more the data we have, the accurately we can train the model and we can get it into use. Otherwise, it makes difficult. Since we do not have much data, so that is the main limitation we can say in present days. So initial cost also to get all this data, we have to invest a lot of things on sensors, like we say IoT. So we have to implement IoT wherever we want to do with the structural health monitoring. We can say also we have skill gap, need for professionals skilled in both civil engineering and AML. I'm sure after having attending FDP, the faculties can have some knowledge about AML so that they can use in civil engineering. So existing challenges for structural health monitoring, if we say, one second. So existing challenges for structural health monitoring are these: material variability. So if we want to do structural health monitoring directly without implementing artificial intelligence, we may face different challenges
Arvind sir,
like material variability. For example, if we want to
Arvind sir,
predict the compressive strength, so
Arvind,
even if we are wearing small amount of materials in that, at the end compressive strength varies. Therefore, we have lot of variability among the materials itself. So that is one of the challenges because we do not use same materials throughout. Even if we change small amount of water or say cement, at the end our compressive strength differs since we have lot of materials used in that. If we come to structural health monitoring, traditional methods are still available which have manual or time consuming process where that is again a challenge because not much technology being used in civil engineering for structural health monitoring though now it is at initial state People are using drones, sensors, and many other things, but still it is a challenge because manual things are much going inside that. Predictive analysis. So it is also a challenge for structural health monitoring. Difficulty in accurately predicting structural behavior under dynamic loading, which will be called as wind or earthquake loads. Since they are not applied directly, they are happening suddenly without any intimation. So during that scenario, it makes difficult for structural health monitoring because it is an unpredictable analysis. Similarly, cost and time, experimental methods for testing materials, like if you want to go for different strengths, then you have to do a number of trials, you have to wait for 28 days. Or if you are going for durability, you have to wait more than 90 days or 1 year sooner. So these are different challenges. If you implement AI/ML models in these, so all these challenges can be overcome. Like waiting for different times, even for cost, we can cut the cost for doing different testing of other things, materials. So to overcome these challenges, we can integrate AI/ML technology with civil engineering for efficiency, speed, and accuracy. Now, AI/ML in concrete mix design and strength prediction, if we take mix design optimization, we can use AI/ML algorithms can analyze historical data to recommend optimal mix proportion for desired strength, durability, and workability. So that we will see one program. I'll do hands-on here only, so that you can understand how we can use AI/ML for mix design or predicting the strength, having different strength. We can check strength, we can have durability, we can work for workability, similar things. Strength prediction also, ML models like maybe regression or neural networks can predict compressive strength based on the factors which we are giving to it. That is features we call in computer language. So here we say just different ingredients like cement, maybe water cement ratio, maybe curing time, maybe admixture or cement, aggregate, anything. So based on that, we will predict the things. Also, example, if we see a neural network trained for concrete mix data can predict 28 days compressive strength with higher accuracy rather than trying again and again with different mix proportions. So, how it can be implemented in structural engineering? Concrete is one part and structural engineering is the other part. So, if you see structural engineering, one where we can apply these are not completely I am covering just for the knowledge sake. There are many multiple things where we can apply ML models or artificial intelligence in civil engineering. So if we talk about structural health monitoring, AML can be used to monitor the health of structure in real time by analyzing sensor data. So as I told you, to implement this technology, we have to invest a lot of amount on sensors to get the data, and we cannot do on small data. We have to have a lot of data and that to accuracy. So if we take scenario, a bridge is equipped with sensors that measures vibrations. So if you want to do structural health monitoring on a bridge, so first we have to have data of vibration, strains, its temperatures from the sensors, and then having that as input, you can design the model which can predict future things happening on it. Means like when it can fail or when it can go maximum deflection in which scenarios. Similarly, crack detection, this if time covers, if time permits, I'll try to cover this. So crack detection in structures. So even having ML model traits, we can detect the cracks in the structures. Having just a photograph, so we can find which type of crack it is, why it is happening that crack, and up to what extent these crack can go. The models can tell us without analyzing that by human beings. So if time permits, we will see this model. So load prediction for structural analysis, like we can use predicting loads or stresses on the structure again by implementing the sensors. Without sensors, we cannot generate accurate model for our purpose. So we should, for example, if we take a high-rise building or a bridge which is subjected to varying loads, and due to factors like traffic, maybe there are different loads acting on that bridge, maybe traffic or wind or temperature changes. So once we have that data, we'll train the model and then we can decide in which scenarios these bridges may have maximum deflection or in which scenario the conditions can be worsened. Similarly, for earthquake also we can utilize then key considerations what we have to do before implementing this. So before implementing AI or any other machine learning model in any domain, the following aspects must be considered. As I was telling, or even Sophie sir was telling, data quality. Ensure high quality labeled data for training AI/ML models. Labeled is nothing but in computer science we have labeled and unlabeled data. Labeled is nothing but whatever you know output. So if you know the output, it is called as labeled. If you don't know, then it is an unlabeled data. So first we should have data quality. We should have high quality of data before training the model. Then along with data, we should have domain knowledge. Combining AI or ML with structural engineering expertise for meaningful results. As if only civil engineer cannot do this or only CSC people cannot do this. So we should have both the knowledges than for having a fruitful results. Then again it comes validation. Whatever model we are generating or we are designing, that has to be validated with the practical things, whether whatever the data it is giving, it is correct or not, we have to validate that. So case studies, if you see, so now I'll start directly with ML based prediction of concrete. We'll see one coding problem. If time permits, we will go to how AI models can be used for threat detection. Uh, that the images which were taken by drone. Then we have machine learning based seismic response. If time permits, we will have some idea on this also. So if we just talk about machine learning models, since many of us, we are new to completely machine learning, so just overview I will tell you. So machine learning models are different models available. So we can have supervised learning, unsupervised learning, reinforced learning. Whatever model is there, we can create models in these ways. Right? So we can create model by linear models, logistic model we can have, support vector models we have, k-nearest model we can have. So we can create models, we can train that, and we can get output from that for predicting values. So we'll see all 5 or 6 models out of these complete models. So machine learning algorithms, different available models are this. We have supervised learning, unsupervised learning, and reinforced learning. In supervised learning, we have linear models, logistic support, and again non-linear models. If we take in this, we have k-nearest neighbor, kernel SVM, we have decision tree, we have random forest method, we have, and if we take regression model. So in regression, we have again simple linear regression, multiple linear, polynomial, support vector, decision tree. So what we will do in the next slide is we will take some data and we will generate all the models and we will check which model is best for us. So having this, so these things we are going to do now. We have to import. First, I'll tell you the overview. First, we have to import the libraries. Like it is like having all the data in hands. To generate graph, we have one library. To draw images, we have one library. So different libraries available in the Python lab. Loading, we have to load the data. Then we have to check the data whether it is correct or not. Then data visualization we will do. So we'll do in the coding meanwhile along with me only. Then you can see different graphs like this. It is called as correlation matrix, how the materials are correlated to each other. So what all these things I have done, rather than showing this, let me tell you how we can do all these things. So it is very simple, everyone can do it. So I hope people are listening. Can I have in the chat box answer? I can go with coding part. May I know how many of are with us? Tirupati sir, can you hear me?
Yes, sir. Yes, sir.
Hello.
Yes, sir. Yes, sir.
Okay, fine. Let us
Sir,
go with the
we are
coding
able
part.
to hear you, sir.
Voice is not audible.
Okay. Sir, my voice is not audible.
Sorry?
Sir, is my voice is audible?
Yeah, now it is. My voice is audible?
Yeah. Yes, sir. Yes.
Okay, fine. Let us go with the coding part. Those who are listening, I'm sure post this presentation, they can do this to their work. So it is very simple. There are different IDs by which we can do the machine learning models. So instead of downloading or what we say installing all the softwares into the system, so what we try to do is we will use online ID which is directly available, which is called as CoLab. It is CoLab. So once we have to go to the CoLab, then coding laboratory, it is given by the Google. Other than that, we have other things also. Offline also we can use. We have Jupyter, we have Visual Studio, Python, and many other things. So I want to use directly online so that many of our civil faculty are not sure about how to install IDs or how to use that IDs. So what we'll do is directly we will open the online ID which is available, that is Colab coding laboratory. So once we open this, we'll be getting like this. So we will go with the new notebook in the drive. Since we are doing this online, the drive, the whatever coding we do, that will be stored into the drive. So let us open the new file into the Google Lab. The same procedure, if you follow, you can also do for your data. What we are going to do now. So this is a platform where we can do the coding part, which is available online. So now what we are going to do. So I have a data like this. Right? You may also have a data for your research, like any X or Y. Here what I am representing is, let us say I have cement, blast furnace, fly ash, water, superplasticizer, coarse aggregate, fine aggregate, age of the concrete, that is for 28 days, 270 days, 365 days. What is the its compressive strength? So if I add all these ingredients at 28 days, this is my compressive strength. So I have set of data like this, around 1030 data I have. Similarly, you can have your data, maybe for transportation, maybe for geotechnical, any other things. So let us say you have your data, experimental data, which you have obtained by doing different experiments. So let us say I have done, not all, I have collected from research papers, then I have some my data. What I'll do is I'll make an Excel sheet like this. So I'll keep this sheet aside, then I'll open this collab, then I will upload this sheet, whatever I have, I'll upload this sheet. Let us say I have here concrete data, I'll upload this sheet into the ID, online ID. So for that procedure is simple, just here we have to go files. So in files, so we have to upload it. So here you can see upload option, just upload it wherever the location is there, please give that location. I will copy from here. So this is the location. If you have in the downloads, you can directly just upload it. So I will upload this. So now I have uploaded my Excel sheet here. Now it is in my drive. From drive, it will, this ID collab will take data from the Google Drive, because in the system it cannot access. Therefore, I am uploading this data to my Google Drive. From Google Drive, it will take all the data. So now I have uploaded my data. You can see here. So once we have uploaded, we have to install some IDs. Don't worry about the write-up here. So I already have here. What I'll do is just I'll copy here, because if I type all these things, time may not be sufficient for me. I'll share this file with you. I'll share this file with you people. You can just do for your data. Whatever experiment or research part you have, just try to do using this file. So let us say, and these are different libraries which are required for doing the graphs part or analysis part, like pandas for this data we require, matplot, it is for mathematical calculations, cbon for drawing the graph, and similar things. So this we have to import the libraries. So just we have to run it. So here we have some error, square, then just run it here also. So once we run it, if it is not giving any error, then the program is correct. Here it is showing it is executing. For the first time it takes time for execute, then it does very quickly. So this part we have to run it. All the things we are importing and we are running this. So that's once we have done this, then what we'll do is we'll import this data. To import this data, we have to use this code. For example, this file I will be sharing with you. You try for your data. Then only we will learn it. Again, so having this, just we have to do the add another column which is code here. So now here I will paste this the code whichever I have copied from there. So what I am doing is hash means it will not take it as a coding. Whatever you want you can write here in this. So if we run that, it will not consider that as a coding if we have hash. If we remove hash, it will consider it as a code. So here we are getting some error. It is showing that just observe the error. Everyone will get this. No such file or directory. So with this name, there is no such data found by the ID lab because name is this concrete data saving. So there is no such file. So actually our file name is different and our file name location is different. So what we'll do is just I'll copy this location, copy path, and just I'll paste here instead of that. And just now execute this. So now you can see our data is completely visible here. What I am doing is I am reading this CSV file or Excel file, reading this CSV file with this name, and I am storing it to the DF. I am giving it name it as a DF. Now I am asking the system or ID to display the head 5. Head 5 means top 5 will be displayed in this. If you want to go with 10, you can have 10 here and then we'll execute here. So 10 things will be displayed. I'll go with again 5 only. Top 5 things has to be displayed again. Execute. So here I can see cement, blast furnace, fly ash, water, superplasticizer, coarse aggregate, fine aggregate, age and compressive strength. Whatever I have in this Excel sheet, now it is uploaded to the Google Colab. So now let us now what we have to do. Let us see here. Now importing part we have done, loading part we have done. Importing is nothing but importing all these libraries, whatever we have these libraries. Next is loading. We have loaded our Excel sheet, experimental part data like this. Next structure. Let us check the structure of the data. Means how the structure it is. Whether there are any null values or blank values. We have to check it because if we have any blank values or irrelevant values, then our output may vary a lot. So now again I will go with a new code here. So what I am doing is just I'll go here. Now I want to check the data of the structure. What I'll do is to check the data. This is the write-up code part. If I type all these things, it takes time. They go directly and yesterday only I did this. So I'm checking data structure now. So if hash is nothing but what I am doing, I am writing here. So if I don't mention hash, it will not be a comment. It will try to take it as a command only. So if you execute it will show error, invalid syntax. So this is not a code part. So what I will do is I just write hash. This is comment. I'm just write. I am telling you what I am doing here. So that part I am writing here. Therefore, as I am commenting. Now I print how many number of rows are there. I'll check. Similarly, print is nothing but tell me. I am getting the output from the coding. Tell me how many number of columns are there. Similarly, tell its information. If I execute this, all informations I can get. So number of rows. Number of rows are 1030, as you can see from here. So here if I check till last, there are 1031. So if we leave the first one, so 1030 rows we have. Similarly, 9 columns we have. You can check here whether we got complete data or not. 1, 2, 3, 4, 5, 6, 7, 8, and 9. 9 rows are there. It is showing all the 9 rows. Next, it belongs to pandas category. Similarly, in cement, we have no null values. Null is nothing but blank values. For example, if I delete any of these 3 or any 4 things, it will show here as 4 null values. But here, since there are no null values, it will show 0 null values in the cement column. Similarly, in the blast furnace column, there are no null values. Fly ash, there are no null values. Float is nothing but like in decimal values. How many decimal values we have? Integers, how many we have? So like that, water, there are no null values. So if you have any null values, you have to fill with the mean value or average value or any other values. The compressive strength also there are no null values. We are checking the structure of the data whatever we have feed it through the system. Now, after checking the structure, let us check any missing values. Are there any missing value? It is not much required. Now let us check the data of the structure. So I want to check the correlation matrix. Correlation matrix is nothing but this part. So if you see this is the correlation matrix. We have, as we have 8 columns, that is cement, blast furnace, fly ash, water, superfly scissor, coarse aggregate, fine aggregate, and all these things. How they are correlated to each other. 1 plus 1 means they are positively correlated to the high extent. Minus 1 means they are negative. They are not much correlated. Like if we see all these values, if you see out of these, highest one is 0.5. Cement and compressive strength, they are positively related, so value is 0.5. Similarly, if we see another value, we have 0.001 minus 0. Minus is nothing but they are negatively correlated. For negatively in the sense, if we take superplasizer and strength of the concrete, let us say this is superplasizer and strength of the concrete is this. Similarly, water. If you take water and compressive strength, everyone knows that if water quantity increases, the compressive strength decreases. Therefore, it is showing negative correlation. So now, how to draw this matrix? Let us check. To get this correlation matrix, just we have to use this code, copy, and we'll just go to our coding part. Then I'll create another step. Everything also we can do in one step, but it makes tedious and will not look ugly. So paste. What I am doing is I am creating data visualization in that correlation matrix I want to get. So SNS, it is also called as heat map. This correlation matrix is also called as heat map. Annotation, it's true line width. However, how much line width you want to keep. Plot title. The title of the graph should be correlation between variables, and plot dot show means it will show the graph after plotting. So it is like this. So this is the correlation matrix between all the elements whatever we have. So let us say I want width 4, just have to type here 4, and again I will execute. You can check the graph. The width has been increased. Similarly, if I want to change the, I have given the name, it is called as correlation matrix. Instead of correlation matrix, I will just give heat map. So once I execute, the name of this will be changed. You can see heat map. Similarly, now I got this matrix. Similarly, everyone can get this matrix or heat map. We can say correlation matrix also. We can say you can get for your experimental data. We are just analyzing the data, how the relation between each variable, fly ash or concrete strength. What is the relation? Whether it is positive or negative, increasing or decreasing. That we can see using this like correlation matrix. Now, so now we will have pair plot. Pair plot is nothing but relation between individual parameter. So let us check that how the individual parameter changes. Again, I have to go code part for this. I'll write code for this. So pair plot here, pair plot is not a code. If I execute, it will show error. You can see invalid syntax. So I have to give hash. Hash thought means it is a comment. I am doing pair plot. Now I will execute. From SNS is nothing but C bond, which we have taken earlier. From SNS, I am going pair plot for my DF, and I am marking it by H, hexagon symbol. So like this, you can get the matrix. Pair plot. If I zoom it, I will show in the PDF here. You can zoom it nicely. So this is the pair plot. Pair plot is for individual along with other. Let us say cement. So it is cement with cement here. Next, cement with here we have blast furnace. This is the correlation between blast furnace and compressive strength. This one. Similarly, correlation between blast furnace and age of the concrete is like this. And fly ash and compressive strength. See here, fly ash, as the quantity of fly ash is increasing, the compressive strength varies like this. up to 80. Similarly, water proportion and compressive strength, it is like this. So each relation, it is pair, it is showing between two things. And like this, if we take cement, and here cement, if we take here, this column is for cement, and here it is water. Cement and water plot is this. Similarly, all the plots you can see here like this. What is this is for compressive strength, and the first one was cement and compressive strength plot, again we can see here. So if cement quantity is increasing, compressive strength is also increasing, like this we can see. So let us go back to coding again. So pair plots we got like this. So just if you want to import in your paper, just copy the image and you can save it to your plot, your paper, and you can write the description about this. So let us go to the next part. We got the pair plot. Next coding, what we want to get. After having this, we got the pair plot. After getting pair plot, let us check the distribution plot. So how the compressive strength is distributed for the frequency. How many times the compressive strength is increasing, or how many times it is getting repeated. To check that, so what we have to do is we have to just take this part. I want to get the distribution plot. I'll take this part, just code this, and I'll paste this code here. So distribution plot I want to get from, again, SNS Seaborn library. I want to get distribution plot for my data frame. Data frame is nothing but whatever I have given in the initial stage. So data frame is nothing but this complete file or Excel sheet. Since I am assigning this to the DF, so everything I will take from that DF only. So DF, compressive strength, bins and colors. Plot Y label as frequency and plot the title of that graph as distribution of concrete. I am asking that plot details like this. So you can get plot like this. You can see compressive strength, how it is varying, how much frequency. If you see in this complete data, around 1030 data, 40 compressive strength is we are getting for the maximum time. Similarly, 0 is less, and 80 also we have compressive strength of 80, but the occurring frequency is very less. If you check this data here, you can see 80, 61, 40, 40, 40. So 40 compressive strength is frequency is high in this data. If I individually, I cannot go individually. What I am doing is to check the frequency, just I will plot this. So I can say around frequency is 0.20 for 40, and it is almost 0.001 for 80 frequency. 100 we do not have any compressive strength as 100, therefore it is not showing. So instead of, if you want to change the name, let us say if you want distribution of compressive strength, instead of distribution of compressive strength, I will just have distribution ratio. Just execute this, the name will be changed here, distribution ratio. So it is how the color, here we can have blue color or we can have red color also. It is R. You just keep on practicing for your data, you will also get this. It's for color. If you don't want to have red color, let us have green color, just click it. You will get green color like this. So this is for color, this is for bins, this ratio line I am getting. So I am plotting only for compressive strength. Similarly, you can plot for other things also. Where from data frame. So distribution ratio, that is about distribution ratio. Next, we'll go to this part. Let us have scatter plot between components. Copy. You can also copy this code. Just go to Colab, write the new code and just execute this. So here it will show error. May I know why it's showing error? Invalid character. So here this sentence should be continuous. Therefore I will write, I will continue here. Then I have here also error. I will give hashtag. Then I execute this. So once I execute this code, what I am doing is I want to scatter plot between components. Figure size. I want to plot the figure of size 13 by 8. So my whatever figure size is there, this size is 13 by 8. Let us say I want to decrease the size. I just type 8 by 8. You can observe here, this will be reduced. Your size will be reduced. Check, it is reduced. Whatever you want, we can change here. Again, we have subplot, plot scatter. We are plotting scatter plot for water, cement and concrete compressive strength only for these three parameters from our data frames, TF. So you can see here how this is varying. This is compressive strength. Here you can see compressive strength. Here it is water, and here on y-axis we have cement. So how, as water content increases and cement increases, what is happening to the compressive strength, we can observe here. So here, if I am increasing the water, let us say from 122 I am going to 240. So if at 240 you can see you have less compressive strength. We do not have much strength here. So like this, yellow color means maximum strength. So yellow color is a maximum strength. Maximum strength we can see here. When the cement is 400 and the water cement is 140. Water cement, we say ratio 140. Similarly, the least strength, which is purple color, when we are having least cement and maximum water. So in this case, whatever data we have, we can analyze using just the graphs. Instead of going one by one, we can visualize all these data using the plots. So just we have not started again implementing. Since we do not have much time, I will do it quickly. So this is again for analyzing part. So now let us from here, we have to train the data. As in machine learning model, the two important thing is training the data and testing the data. So we have this Excel sheet in which we have around 1030 sets. So I will not train the data, my data for all the values. What I will do is I will divide this data into 70 and 30. So 70% data will be used for training the model and 30% data will be used for testing the model. Whatever model has been generated, whether it is correct or not, it will test by rest of the 30. Let us say I have 10 apples with me. I will show 7 apples to my child. I will train the child with the 7 apples. I will show different apples to that child, and I will train that it is apple, it is apple. Now 33 apples I will keep aside. Next time I will ask that kid to tell me what is this. So in that way we are splitting the complete data into training and testing. So for that we have simple code again. So we do using this thing, this code, train data, test data. Don't go much into the syntax, just try to use this. So let us say this is the syntax which is already available. So what I am doing is, so from here onwards, we are first dividing our data, splitting our data into training and testing. The data set is divided into 70 and 30. Generally, we do it for 70 and 30%. If you want, you can go it for 50-50 or 80-20. The more we train, the more accuracy models will be. In that sense, we cannot train the model for 100% because if we show same values, the model is already trained for that. So we cannot again ask that. So now here, this part, this. So we'll just get into one line. So this part is crucial in generating the model. What I am doing is here, test size I am keeping it to 0.3, means 30% I am keeping it for testing. Obviously train will be 0.7, that is 70%. If you want to keep test size to just 40, you can just type here 0.2. So I'll go with generally 0.3, 30% I will keep for testing, rest will be for training. So this train X data. So X data, in this we have all these as X. So what I am considering is I am taking all these parameter as X and my dependent is compressive strength. This is Y. So same thing again, Y is our output. Let us say compressive strength, I want to keep it as Y, and these all are 6. My compressive strength depends on all these parameters. So I will take this, the same thing in the coding. So here training model X for X in train columns, the coding this time explicit, not in concrete compressive strength, means except concrete compressive strength and age of the member, I am taking X parameters, rest all are parameters. Similarly, Y, in case of Y, only I will take concrete compressive strength. So train Y is my output is my compressive strength. Similarly, test and train, then we will just execute it. So here we have syntax error again. Here we have to give a hash since it is a comment, it is not a coding. I will execute. There is no error, means our data is split into training and testing. The training is 70%, testing is 30%. Here you can see the data is divided into 70 and 30% splitting between the training. So after dividing the data, just we will go for the model generation. So first model I am taking, I may not take all the models. So here first model I am taking multiple linear regression. So next, having this, let us generate the first model. For I am generating the first model. So model number 1. Hashtag model number 1 multiple linear regression fit model. So just this is in the next line. I'll run it. So my model has been generated. I have developed the model which is called as multiple linear regression. So prediction for L predict test X. Similarly, M1 model, I want to check the score of this model. Next, I want to check the accuracy of this model. I want to check mean absolute error of this model. How much is the mean squared error of this model and root mean square of the model. So just I'll print this. So using this linear regression I have initially imported here. You can say here linear regression. So from that linear regression library, I am generating the first model which is called as multiple linear regression. So fit train data, train X data, train Y data, then it will predict some data. So after predicting, it will give me accuracy. What is the accuracy? What is the mean absolute values? Here we can see the values. Accuracy of this model is just 63% for this training and testing data. Similarly, mean absolute error is 7.7, mean squared error 93. Generally, if it is 90, we can take it as a good value. If it is less than 90, then we may not take it as an accurate measure. R square value it is 9.6. So for this error, so having this data, let us get a plot training and test. What we say predicted. How much model is predicting and how much accurate values are there. So for that, what we'll do is we'll take this feature importance. Feature importance I'll take it for 1 month. Means in this model, which features are much important. So if we take like this, so now in this model, I want to check the feature importance. So which feature is how much importance giving in this model? Which model? Our model number 1, multiple linear regression. So here if we have, this is the thing. Cement, we have cement, fly ash and all other things. Cement is this much important, 0.1% importance for predicting the strength. Similarly, superplasticity is having much importance as per this model for predicting the compressive strength. Similarly, water, we can say aggregate. Water, you can see -1, means water is increasing, compressive strength is decreasing. Therefore, they are inversely proportional. So this is how the important in this model. Now let us check the predicted values and the actual values. So model has trained its 30% values. Now it is checking how much strength it will give for next 30. I will go with code again. Here. Code here. Replace the same thing and write that since it is a comment. What I am doing, I want to plot the true values versus predicted values predicted by model number 1. So I just do it for only 25 columns. Just a sample data I am taking, not all the values. So actual values and predicted values I will take, and I'll also plot. So these are plot. I want to have a grid plot with major axis, minor axis, and width of the line is 0.5. Color may be green. Similarly, for plot grid, we have minor axis also I am taking, line style like this, width also I am taking. Just I'll execute this so I can get a plot. Actual are indicated by blue color and predicted by orange color. So here you can see, I am taking only just for 25 columns, not all the columns. The actual value is here 27, but predicting is much 40. Therefore, the accuracy is not high for this model. You can see here similarly for other value. If you want to change the color from green to yellow, you can take here yellow and then execute. You can have, so like we have grid colors. So if you don't want to have grid colors, just we can off this. Line width also you can change it. Instead of this, you can have 0.2. This is about all decoration purpose in the graph. This all this. Similarly, figure size, if you want to more size of the figure, let us give it 12 by 7. The size of the figure increases. So this is just about decoration purpose, but the actual coding is only this part. That's it. This is a small code for plotting the predicted values versus true values. So now, similarly, I have 10 models with me because time may not permit for this. Just I will go with here only PDF. So here this is for first model. If I similarly, I will take a lasso model. Lasso model, that is model number 2. You just copy this model and I will check what is the accuracy of this model. How much accurate is this compared to the other model. I will go with coding, paste one model. So this one is in the 7th line. And run this. So now the accuracy of this model is again 63%. Mean absolute value is 7.7. Since the data is not much accurate we have, the accuracy of the model is not good for that given data. Mean squared error here is 93%. Similarly, we can get the plot also, how they are feature selection, which parameter is important for this. So if we can plot this plot also, which is actual versus predicted values as per this model, second model. So similarly, we have KNN model. Third model, KNN model, we can generate, we can check the accuracy. If I check the accuracy for that model, it is 64%. I can have the predicted versus actual plot also. Now the model number 4, I will have SVR. Model number 4 is SVR I am taking. For that, similarly, model number 5, like this, it is polynomial degree 2. For this model, the accuracy of this model is 75. That is 75%. It is little bit better than the earlier model. If I take polynomial degree 3 model, for that also accuracy is bit increasing, that is 79% for this data. So again, prediction and expected values will be increased. Now if we check model number, if we check, we can compare all the models at a time like this also. Model 1, model 2, linear model I have, polynomial model we have number T, or polynomial model number 3 I have, lasso model I have KNN, K nearest neighbor, and SVM, support vector mechanism. Like this, I can check all the models comparison like this. So we can see the best one is this one, linear. Almost all are same for this data. So how many models we have generated here? 1, 2, 3, 4, 5, 6 models we are generating here for this data. And we are checking which model is best suited for our data. So from the results we can see this model is okay for our data. Again, we have different models. You can generate all the models and take the suitable one. So having all the graphs drawn, once we include in our research paper with the experimental values, the paper will have plenty of chances getting accepted in any of the good ACI papers. So time, I have already exceeded my time. So I am not writing coding part for other models. If you want, I can share this code with you for your data, which you can practice it for your data. So that's it. I want to share it today. The thing is, if you practice for your data, then only we can understand machine learning model accurately. I could have explained all the just what I have done, but what I wanted to have participant is they have to learn completely rather than listening. How we can implement for our work. So that's the reason I have taken a small part of coding. Tirupati sir, or Sai sir,
Yeah. Thank you, sir. Thank you so much.
we can take questions.
Yeah, yes, sir. Just go to chat box, sir. There are few questions.
Yeah, definitely. I'll share code with you rather than sharing what I suggest you to practice this code for your data. Then only we can learn. This coding part is much easy until we go into that. So as the participants are requesting for sharing the code or hands-on, actually in 1 hour we cannot have hands-on experience. Hands-on experience, at least we should have 2 to 3 days to get complete hands-on experience and have wonderful learning experience. So only thing if you want to learn machine learning is you should learn Python language. That is the sufficient one. So why the question is why age is excluded in independent variable test. If you want, we can take it also. I thought it is not much important or it may create bias. Bias is nothing but differences between the results. Therefore, I have excluded that because some results are for 28 days, some results are for 90 days, some results are for 20 like this 28 days. We have 360 days, we have 90 days. So there is much gap between the days. Therefore, I am neglecting it. If you want, you can include. Maybe accuracy again decreases. So we have to avoid the biased data. You can unmute your mic and you can ask the questions, participants. You can unmute.
Sir, one more question. Yeah, in
Yeah.
the group.
What should be a good accuracy value? As I'm telling from the starting that the more the perfectly you train the model with accurate values, your output will be exactly accurate. Like we are training our own kid for good behavior and bad behavior. If you are training your own kid for good behavior, obviously in future it will have good results only. Since in this data I have collected it from research papers, I may have a lot of what we say bias in this. Some author may say for let us say 47.5 cement I am taking. For that cement, the strength may be 42, but other author for same 47 may say 28. Therefore, there is a much bias between the trained data itself. Therefore, accuracy is less. This data can be handled, but for the different models. So I made the ML in very simple way. What you have to do is do no need to install any Anaconda, any Python or any ID, let us say Jupyter or any other thing. Just to go to Colab, upload your own data and then just start coding. That's it. If you have any doubts, you can just go to the chat GPT itself.
Hello, sir.
Hi.
Sir, I would like to ask a question whether training data can be generated using any FEM software and
Yeah, we
then
can be
prediction
no.
can be done.
Yeah, no need to go again to FEM also. In Python itself, we can generate using just one code.
Okay. If
Only
I
one
am,
code we can generate, but that is not the actual data again.
okay,
Actual data we have to get it from the experimental values.
yeah, if I am going for any geotechnical problem for
Yeah,
prediction of any capacity of a foundation, and
yeah,
if I am generating training values using FEM,
yeah.
then using that value and validating the actual experimental or field values.
Yes, we can do it.
Yes.
We
Okay.
can do it. We can generate it, but once it gives the output, we have to check again experimentally. That will be a good work again.
Okay. And if you could please share that PDF also, it would be very good.
Yeah, I'll share that video because it will be helpful for you. I know that is the main thing to learn the coding.
Oh,
And
oh,
if at all we are getting any error in that, no, just you can copy paste that error in the chat GPT. It will give you the solution to all the participants.
and if you are installing Python, is there any for this purpose? If you are using Python, installing Python, is there any system requirement? Means,
Yeah, we have system requirement since we have to do coding. We have to import all the libraries. We have minimum 4 GB is required for that Python.
okay,
And Python directly we cannot include. We have to just as you can see, I have installed many libraries prior to doing the coding. So
Okay.
that coding is available in the Anaconda. Anaconda is a complete package. So in that package you have all the things. So individually Python, if we install Python, Python will again take from that library, C1 library, maybe data frames, all that extra things are required.
Okay. And in your opinion, how much time would it take to learn Python or for this purpose?
For this purpose, today only you can do this coding part.
Okay.
I can say only 1 hour is sufficient for you. So if I want to show you, just see here, whatever code I have pasted here. Let us say I have made some mistake. I hope you can see my screen.
Yeah. Yes.
So let us say I'll just, instead of train X, X test, I'll just type it Y, and I will just give the execution part. It will throw some error. Now I don't know what is that error, right? So what
Yes.
I'll do is just I'll take this coding part, copy. I'll go to chat and I'll post this question. This code I will post it first, and then I will code this, post this error. Okay.
Okay.
Now it will say some mistake you have done. You have name error. Your code because test y is not defined. Okay. Okay. I'll not go into that. What I'll do is just I'll copy this. I don't want to go in that. I have made some mistake I might have done. I don't want to see that mistake. Now I will post this code here. Now I will delete this one, code it, and just paste this. Whatever ChatGPT is giving. Again, I have same solution. See, it has given me the correct code.
Okay.
So I can say you can learn in 1 hour itself. Having this code, having a proper guidance.
Okay. And what about training data sets? Is there any particular number we should be aiming for?
The more you train, the accurate model you can get it. That's the reason. Only thing, the demerit of using AI/ML in civil engineering is we should have lot of data. For example, I have also had that, but I could not present that because of time. Let us say I have cracks. First, I have to train the model. This is the crack. This is the reason. This is the crack. This is the reason. This is the crack. This is the reason. I should train it for lakhs of data. Next time, if I just show the crack, if I click the image and if I show it, it will say due to this reason this crack is getting, and this may be the solution. It will also suggest you until you train with plenty of data. Challenge is this.
Okay. Thank you, sir.
Yeah. Any other doubts are most welcome. I am here to help you for learning the AML because uh, without AML there is no civil engineering future. If you have just core knowledge, it is not sufficient.
Hello, good afternoon, sir.
Good afternoon, Chitra.
Sir, basically structural health monitoring or structural health issue problems are non-linear basically.
Yeah,
So is this ANN will be helpful for solving those non-linear issues?
ANN was discussed by Sophie sir, I guess, artificial neural networking. It is one of the part again in AI/ML, one of the way which you can use. But again, to do structural health monitoring, we should have lot of data which is obtained by IoT devices, Internet of Things, or sensors. Maybe vibrations, maybe stresses, maybe deflections. You have to have continued data from time to time. So first we have to
Okay.
train the model with that data. So then future you can predict. So again, for collection of that data, we have to install sensors and we have to wait it for long time. These are some challenges, ma'am.
Yeah, yeah.
That is the reason it is not being implemented till date. If you see share market, we have data from 20 years, that is 2 decades. So that it can predict. Even if we go to the websites for, we say what like climate data we are collecting from 30, 40 years. So having that data, you can predict for next 40 years also. But whereas in civil engineering, we don't have any data to train the models.
That is the basic issue most of the time, sir.
That is the challenge.
Thank you, sir.
Yeah, madam. Any
I
other
think,
questions are most
yeah,
welcome. Here, interaction is
one,
much important than listening. If data, Bhavani, if data is not sufficiently available, how to create data? What parameters need to look into create data? See, if we can create any data using the coding itself. Randomly also it can create, but we don't know whether the data is correct or not. For that reason, we have to first do the experimental part, have that data, and having that data, we can train the model. I hope I gave the answer.
sir, one more question left.
Yeah.
Somebody asked, suggest few web links, record videos, textbooks for learning AML. Yeah. So if you have any
As per my
sources,
experience, having this knowledge, one guidance is sufficient for us. No web links or no recorded videos will exactly give solution to our problem. We have to start from the starting itself. So what I suggest you, just you learn the coding. If you have Python grip in the Python, which you may learn in 1 month, rest everything we can do it. There are complete YouTube videos available, complete course on Python, like Apna College is there. From there we can learn the Python language. Once we have Python language, we can do anything. Syntax is not important. Just I have shown you. For us, the main guru is ChatGPT or DeepSeek also you can say. Any problem we got, just copy paste it. It will give the solution. We need that's it.
okay, any questions from the participants?
I think those who have listened or seen the today's lecture, they may get some confidence to do the coding. They feel that coding is not much difficult. How to select the model? There are different models. Until you get satisfied, you can just do the generation of models. As in the starting slide itself, like here I have shown you. These are different machine learning models which are available. So out of these models, we can create, if these models are not sufficient, we can combine these two models. That is called as hybrid model, which generally CSC people will do. We can have our own model also. Until we get accuracy, till then we have to keep on doing for all the models, as I have done for 6 models here.
Any questions from the participants? As requested, we'll share this our mail ID. So if you have any questions, you can contact Dr. Arvind Kumar sir directly
Yeah, always
through mail.
available,
Yeah.
free to help.
And sir, as you said, please share the code. So I will share with all the participants. Just mail to HODC sir.
Yeah, yes,
So I will share with all the participants. Just you can practice, and if you have any questions, then directly you can contact to Arvind sir.
Yeah.
Yeah.
So in future, if we have workshop hands-on experience, that will be much benefited.
I think the one more last question, probably how to ensemble the models. So somebody asked the chat box, Chandra Mohan Rao sir.
Ensembling again, it is a different technique. We have to go beyond the coding.
Okay, thank you, sir. Thank you, Arvind, sir, for providing great insights into artificial intelligence and machine learning applications in structural engineering. Uh, with this, we'll close the session, and tomorrow at 2 o'clock, we'll start the third session. And feedback links already shared for lecture 3 and 4 to your mail. If anyone have not received, just message me in the group or mail me. Okay. By please submit the feedback link by 9 o'clock, 9 p.m. today. Thank you all for your participation. Thank you, sir. Thank you once again for accepting our request and delivering the lecture.
Thank you. It was my pleasure.
Thank you, sir. Thank you. With this, we are closing the session. Thank you, sir.